Hello and welcome back. We're going to do the second part of lesson 12, I believe it is today. All right, so now we're going to talk about continuity. So we talked a little bit about limits in the last one. So continuity is basically the idea that the limits and the values of a function are the same over a set amount of space. So last time we talked about limits being what the function should be, and the values being what the function actually is. So real quick, let's go to the board. Just so we can look at an example of both. So let's say I have the function. Ooh, that was definitely not what I wanted to click. There we go. All right. So let's say, brush. So let's say the function is x times x minus 3 over x minus 3. So if we were to actually try to plug in 3 for this function, we would get an error. We would get does not exist. And the reason we would get does not exist is because the bottom would be set equal to 0. However, if we did the limit as x approaches 3 of the function, we would actually get 3. And the reason for this is because the limit means we get to use the rules of algebra to cancel the x minus 3's the way that we actually should be able to. So then we would just have x, and of course if you plugged 3 into x, if x is 3, well then your answer is 3. 3 is 3. Fabulous. So this is what we want to avoid when we have something that is continuous. So this function would be what we'd call discontinuous. Discontinuous because there is a single place where the value of the function and the limit of the function are different. There's a place where using algebra, we could make this function a little bit simpler and remove a so-called discontinuity. So if we were to look at the chart here of this discontinuous function, let's do a little bit of erasing. So actually not erasing, let's move these to the side. So if we were to examine the point where this is happening, where the limit and the function are not working in sync. So 1, 2, 3, 1, 2, 3. So this function works pretty much like y equals x all the way up until we hit 3, and then there's a hole there. So normally what I'll tell people with continuities is that if you can draw them without if you can draw the function without lifting your pencil, then it's continuous. And a exception to something like this would be a function like this, where you have to, pick up the pencil to go from the bottom to the top. So obviously this guy isn't continuous because there's a break right there. We wouldn't be able to use that function. We'll look at some examples of those in the algebra, but we'll also look at the big graphs. So, but over here, the one exception to this is holes. So if there's a hole, you can technically draw it, if you're really careful about it, you can draw it without having to lift your pencil, but it's kind of hard. It's much easier to just go and then pick up your pencil and then start drawing again. So with holes, it's not very easy to do that, which is kind of the signal to your brain that, oh, there's a hole here, there's something that's going wrong, and now I'm going to need to mark this as discontinuous. So it's discontinuous, but it's only discontinuous at x equals 3. So where a function is discontinuous is also very important, because this function only has its problem if we try to plug 3 into it. So if we don't try to plug 3 into it, then it would be continuous everywhere else. So if I asked you for any discontinuities, so if I wanted discontinuities on the interval from -10 to 1, well, then we'd look at this and we'd go, oh, well, there's not any discontinuities. I mean, that would cause a problem if I plugged in 3, so like I can't plug in 3. But you didn't ask me for 3. You don't care if 3 is a part of this little setup, because we are only looking strictly on the number line from -10 to +1. So on that line, this function would be continuous because there's no discontinuities anywhere between here. It would just be running, the straight y equals x function. If we kept it going, so I'm going to do this in, I'll do it in blue so that we can see it over the, well, actually, I'll just erase the reds up there, so come on. Let's get rid of some of this red. Too much red. I like red, but sometimes you can have too much red. Okay. So there we go. So if we kept running this function after 1, it would have a discontinuity at 3. But because that discontinuity is outside of where I'm checking, it still exists, but it's way over here, we would say that on this interval, the function f of x is continuous. So it's continuous from -10 to 1. That's perfectly fine. We know that it's continuous there. But if we were to look from, let's say, 1 to 5, then we would say it is discontinuous because, oh no, now the limit, and the limit is, approaching from the left and right, and the actual value of the function are two different numbers. Now we have an issue, right? That or either that or the value just doesn't exist at all. And so if the value doesn't exist for the function and it does exist for the limit, then yeah, we've got a problem here. So this would be discontinuous if we looked from 1 to 5, but it would be continuous if we looked from -10 to 1. And the reason is that we have 3 inside here, and that's our big stinker. That's the one that is going to mess up our continuousness. So we would be continuous over here. We would not be continuous over here because there is a hole in the function. So now let's look at a different function now. Let's look at one that's discontinuous somewhere else. So let's say I have the function 1 over, say, x minus 3 times x plus 5. Okay, so this function is going to look something like this. So at positive 3, and at -5, we're going to have issues. And if you're wondering how I came up with those numbers, basically what I did is I set the bottom equal to 0. So I did x minus 3 equals 0. So that gives me x equals 3, which is this line over here, x equals 3. And I did the same thing with x plus 5. So if x plus 5 equals 0, then x equals -5. So there I have very clear discontinuity. So if I tried to run this function, I'd be going like this, and then I go down, and then I would be getting, or actually, hold on. I want to say, so let's see. Let's actually plug that number in. So if I plugged in, say I plugged in -6. So -6 minus 3, so that'd be a negative number. -6 plus 5, that'd be a negative number. Negative times negative is positive. So my apologies, it would go up that way. And then if I plugged in a number bigger than -5, so let's say I plugged in 0. So if I plugged in 0, 0 minus 3 would be negative. 0 plus 5, that'd be a positive number. So actually, it would be down here. My sincere apologies. I need to draw this correctly. And I know if we plug in positive numbers, we're going to get positive. So it's going to look like that. So this is what our function looks like. This is what f of x looks like. So let's say we want to do a continuity check. So we want to see if it's continuous on, let's say we're going from -2 to 4. -2 to 4. So is it continuous there? So we're starting off at -2. So here's -2. And we're going to check. So it is continuous at -2. So it's still good, still good, still good, still good, still good. Oh no! We just hit 3. So now there's a break. And then we go on to 4. So no, this would not be continuous from -2 to 4 because we have a break in between those two numbers. Whereas, if I tried something a little different, so let's ask now, what would it be continuous on, see if it's continuous on the interval -3 to 1. So if we check between -3 and 1, so here's -3. So if we check -3, we keep going, keep going, keep going. Here's, let's say 1's right here. Well, what do you know? There's no discontinuities there. So even though it's discontinuous on this interval, it is continuous here. So whenever you're being asked whether or not a function is continuous, if it does have discontinuities, sometimes you have to check and see. It's like, okay, well, where are those? Because every now and then we do have functions that are discontinuous, but we want to use them anyway. So as long as we don't break the rule of algebra, as long as we don't get these discontinuities, if we know where they are, we know where we can work. So we can't work at -5, we can't work at 3, but we can work everywhere else. That is important information that we can use moving forward. All right, and then so that's everything about continuity. And so let's talk for a second about discontinuities. We're just going to talk about the types of discontinuities. So there are three kinds of discontinuities. There's a kind called infinite, removable, and jumps. And each one of these has a very specific identifiable feature that'll make them easy to spot. So let's go ahead and go back to the board. And let's look at one of each. So let's start with infinite. So infinite is very straightforward in the sense that it's a discontinuity that has infinity in it. So let's say we have 1 over x minus 2. So if we drew this chart, here's positive 2. I'm not allowed to touch it. So if I go here, and then I got to go there. So this is what this function looks like. So basically, if I plug in 2 here, I'm going to get 1 divided by 0. And that's going to take me either to negative infinity, or that's going to take me to positive infinity. So this is what's known as an infinite. So an infinite discontinuity. And the reason why is because, you know, the before part of the function is going to go down forever. The after part of the function is going to go up forever. So if you can't remove it using algebra, and it's just a normal function where algebra is not going to help you, that's going to give you an infinite discontinuity. Because if you go to graph it, what you're going to see is that function goes on infinitely. You're not going to be able to see where it stops because it never stops because it's infinite. So that's infinite discontinuities. Now let's talk about removable discontinuities. You've actually seen a couple of these. These are actually quite nice. They're very simple and straightforward. So let's say we have x over x plus 3, and on bottom we have x plus 3. So I think you can already see where I'm going with this. So according to the rules of algebra, I should be able to cancel these out. So that would just make my function y equals x everywhere except for boop x equals negative 3. So if I plug in negative 3 plus 3 is 0. I can't divide by 0, so there's going to be a discontinuity there. But here's the cool part. So as you saw, I was able to remove this discontinuity using algebra. So if I put a limit on it, I know where it's supposed to be. So I can imagine in my mind, you know, how I would cross that. Well, if I plug in negative 3, well, I'll just ignore the other two and just pretend it's negative 3, because that would give me a value that I can work with. So this is what we call a removable discontinuity. And the reason it's called removable is because you can, well, remove it using algebra. So if you can cancel out whatever's causing the discontinuity using algebra, it is considered to be a removable discontinuity. Okay, so that's removable discontinuities. And this last one we're going to talk about is a jump. And so for those of you who've seen all the lessons, this is going to be a blast from the past. So we've got a split function. So split functions tend to be very interesting. So x is less than 3, and let's say we have x squared for x is greater than or equal to 3. So when we go to graph this thing, so this thing is going to be totally different from what we were doing before. So we got the function 2 times x, and we're going to have that up until we hit x equals 3. So we're just going up, 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 up. Oh, now there's an open one. And then we got to do x squared from there. So 2 times 3, that'd be 6. So 3 times 3, that'd be 9. So we actually have to jump way up here before we continue on using the x squared formula. So this is an example where there's no algebra to be done, but this is clearly not a normal function. This is a split function we're dealing with. So anytime the function splits, we can see that we could actually get back on track in terms of continuity anyway if we just jumped from the first part of the function to the second part of the function. We can actually see how big that jump is. In this case, the jump is it's 3 units tall. So anytime you have a split function or the gap between the two continuous parts of the function is visible, call this a jump. This is a jump discontinuity. So if you could fix it just by doing a simple jump between the 2 points, then the discontinuity is referred to as a jump discontinuity. And that's really all there is to jumps. Most of the time, if someone gives you the algebra or the formula behind a jump discontinuity, it'll be very obvious that that's what's going on. Because even if these two did go to the same number, it would still be considered discontinuous because the left side and the right side could be going to different places. So that would be another discontinuity. So very easy to spot discontinuities of the jump variety. So that is discontinuities, and I believe that's the end of, yeah. So next time when we meet, we're going to talk about what kind of discontinuity is here. And depending on how sharp you are in algebra, you might already know the answer, but we'll also go over a couple other examples. So if you're watching this video, I hope to see you there at the synchronous hours, and hope you're having a great day, and I will see you later. Bye-bye.